Hello, everyone, and a big welcome to our POSPac Complete webinar with the title Beyond the Base Station, POSPac Next Generation and Hybrid Aerial Mapping. Today, we are showing you the top news about POSPac Complete and share insight on hybrid aerial mapping. I'm Nico, POSPac Complete and POSPac Cloud Product Manager. And I'm very delighted to be joined today by Dr. Mohamed Mostafa and Bernhard Schachinger from Vexcel Imaging. So Bernhard is actually the head of applied photogrammetry, data and workflow at Vexcel Imaging. Since 2008, he has leveraged his geoinformatics background and expertise in imagery, LiDAR processing, and specifically UltraMap software to lead global customer projects and geospatial research. And then we also have Mohamed here. He is the lead technical authority at Trimble Applanix. He holds a geomatics PhD and brings over 30 years of multi-sensor systems expertise. He's an internationally awarded industry leader with over 300 publications and 3 decades of scientific organizational volunteering. So I'm very happy and very delighted to have both on board today. And we'll start the discussion about the details a little later. So first of all, some words about the agenda. So we'll focus on POSPac Complete, our new generation. And then we will dive into the case study, or let's say case studies about hybrid aerial mapping before we go to the summary and a bit of a Q&A session. Now, some words about the logistics of this webinar. The presentation will take approximately 60 minutes. The webinar will be recorded and shared with you. All attendees are muted. Should you have any questions, please feel free to enter them in the Q&A box at the bottom. We will try to answer them after the presentation, or should we not have sufficient time, we'll definitely answer your questions offline via email. So let's focus on the first topic, POSPac Complete. So yeah, Applanix POSPac Complete is the next generation of Trimble's post-processing software for mobile mapping purposes, leveraging the core technologies, Trimble's core technologies, which is Trimble ProPoint GNSS, Trimble CenterPoint RTX, and Applanix IN-Fusion Plus. This POSPac Complete package replaces POSPac MMS and POSPac UAV, the previous versions of our POSPac solution. And this one, as you can see, bundles both into one offering. Now, this POSPac Complete, or let's say the heart of POSPac Complete, is the Applanix IN-Fusion Plus engine, which is an advanced multi-sensor aided inertial engine that integrates data from various resources to provide continuous and robust spatial knowledge. It supports all latest GNSS signals and frequencies, and it fuses measurements not only from GNSS and inertial sensors, but it can also take into account data from sensors like the LiDAR, cameras, odometer, to deliver precise position orientation. So the engine is really designed to support other aiding components, such as visual odometry, or think about map aiding. So this technology offers robust accuracy and reliability, particularly in challenging GNSS environments, like urban canyons or areas with dense foliage. Now, what we've added here in POSPac Complete are the additional processing modes for the IN-Fusion Plus engine for the airborne sector when it comes to single base processing, but also PP-RTX processing. We actually removed the legacy IN-Fusion modes. We only kept smart base in. The rest really sits with the IN-Fusion Plus engine. We also improved significantly the post-processing speed in the airborne sector as well as in the land sector for IN-Fusion Plus single base and PP-RTX by a magnitude of about 30 to 50%. It really depends on the application, the data that you load, but on average, it's around 30 to 50%. We also achieved a bit of a better performance when it comes to single base processing, 5% horizontally and 25% vertically. And in PP-RTX mode, it's about 10% in 3D. Now, what we've decided for POSPac Complete is to put the post-processed RTX very centric in our offering. I think most of you have heard about RTX before. So we are leveraging Trimble CenterPoint RTX technology in post-processing mode. And as you may have heard, so this is basically based out of a Trimble network of stations tracking data day and night. And all of the data are processed in the control center, and via a smart algorithm, it creates a set of correction data, a correction stream for the rover that is applicable in real time, but also in post-processing. And this is applicable worldwide when it comes to post-processing. Now, core benefits are obviously that the user does not need any base stations. If you decide to post-process in RTX mode, you don't need any base stations. And also a core benefit is that since we have full control over the correction stream, we obviously know what the datum or frame is that's behind it. So there's no doubts anymore, doubts that you would typically have with base station data. And of course, since it's also readable in real time, when it comes to post-processing, the correction data is available within minutes after data collection. Now, I decided not to dive too much into the technique of PP-RTX. I prefer to show you some real-world data and the performance that we can achieve. So first of all, let's look into the UAV segment here. You can see here a table where we compare the PP-RTX accuracy from the former engine versus the new IN-Fusion Plus engine. And this is out of 66 UAV data sets in the global region. RTX is split into into a fast region and a global region. So this data sets or the statistics here is purely from the global region. And the comparison in terms of the accuracy or trajectory post-processing was always against a single base station that was nearby to cancel out all of the GNSS error budget or keep it very small. So what you can see here is that we came down from 2 to 4 centimeter horizontal performance to 1 centimeter with the new engine on the horizontal side, and on the vertical side from 9 to 5 centimeter. And that equals an improvement of 100%, basically. Another example I wanted to share here is a case study from the mobile mapping sector. For that project, we used a Trimble MX60 mobile mapping system in a moderate open sky terrain. And baseline length was below 5 kilometers, which serves as a reference. And we collected 3 independent data sets, so like 3 missions at different dates, different time. And they covered each like 3 loops of 1.2 kilometers LiDAR data acquisition. And over the entire test field, we had ground control points laid out. And what we did is we post-processed the solution with the traditional single base approach and then with the PP-RTX approach. We calculated the point cloud and measured the ground control points against it. So the standard deviation that you can see here at the bottom for the horizontal component, where we used 13 ground control points, was about 9 millimeter for single base and 12 millimeter for PP-RTX. On the vertical component, we even used more than 30 ground control points and held it against it. and we saw 8mm single base accuracy and PP-RTX the same size, so the same magnitude, 8mm. Now, if you look at that, you can round it up to 1 centimeter, and you can see how well the PP-RTX processing matches the traditional single base processing. And in that context, you can say that PP-RTX replaces single base also in the land mobile sector. Another case study here was done with yellow scan. So that's based out of a UAV flight with a VX20 system equipped with a Regal Minivook system. And the flight was above, well, 100 meter above ground, actually. The expected system accuracy is typically 2.5 centimeter. Same principle here. We processed the trajectory with a single base that was in a radius of 1 kilometer, and then we processed the trajectory in PP-RTX. We calculated the point cloud and then measured against ground control points. So again, this is an absolute accuracy that you can see here, same as before. We used 10 ground control points, and the performance that we achieved really only in the vertical component, because that's the important part when you think about LiDAR scanning, was about 1.3 centimeter RMS and single base and 1.9 in PP-RTX. And the standard deviation a little bit lower. There's a little bit of a difference between single base and PP-RTX, but that is negligible. So again, also in the UAV market segment, PP-RTX becomes very powerful and can replace the legacy post-processing mode single base. Now, a very exciting thing to share with you relates to our latest POSPac Complete release, which only happened last week. This is POSPac Complete 2026.04. And what we have included here is a new algorithm. We call it code bias-based GNSS outlier detection. Pretty long name, but it's very effective. It improves IN-Fusion plus PP-RTX processing in canyons, in urban terrain, significantly. It can suppress standalone position anomalies by 88%, which leads to a 1 sigma performance boost for the aspect file of 44%. And that is 1 sigma. If you look at the table on the right side, 2 sigma is even stronger. It's 58%. So this is a very, very strong improvement and performance boost. And the statistics is really out of 65 hours of real world data collected across Toronto downtown by 5 different GNSS INS systems. And yeah, the comparison against this one was always by using a single base station solution. And just to say, for this new algorithm that's embedded here, we have even 2 pending patents. Now I'm coming to another topic. Part of this POSPac Complete project for this new generation was to focus also more specifically on the user experience. So a great user experience leads directly to user satisfaction, and it deserves as much attention as engine performance. So this is especially true now, as modern users are often not the same technical experts they were in the past. Now, what we have included here is background maps. We're supporting topographic maps as well as satellite maps. And over the maps, you can see all of the downloadable base stations that we support. And this includes not only core stations, but all the Trimble base stations. So we have a database of more than 13,000 stations that can be leveraged. Now, one other important thing that we focused on here is the so-called project wizard. So we wanted to keep the things very simple for the user. And we broke the wizard down to 3 primary steps to process your GNSS INS data, which is import, process, and export. And along that line, you will see that we have new icons, colors, really a better look and feel. Now, when you load the data, the data will be overlaid over the map, either topographic map or satellite map. And then when it comes to the second step of the wizard, it's going to be post-processing. We have also an algorithm there that automatically detects what is going to be the best post-processing mode. The software will make some suggestions, as you can see, 3 suggestions here, but will also make a selection for the user. So the user can verify that if he wants, but he can also simply click and move on because the software is smart enough to figure out what the best processing mode is. And finally, step number 3 is to export your solution. So that could be like the SBET file in your target frame, or it could be the XT orientation parameters when it comes to photogrammetry. And of course, very often the user also want to export the QC report with some tailored plots for the analysis of the results. Now, one other interesting technology that resides in POSPac Complete is called IonoGuard. And IonoGuard is the latest Trimble technology to mitigate ionospheric scintillation effects. So you probably heard that we've been running through another cycle of high solar activities. They reached a peak in 2025, but we have an extended season of it, so it even goes into 2026. That cycle repeats every 11 years. Well, if you have that high solar activity, that impacts GNSS position performance, and it degrades the GNSS position performance. And it can degrade it by going up to meter level of accuracy. Now, with this IonoGuard, this is going to be mitigated, the problem is solved, and we support that in single base processing as well as in PP-RTX processing. There's also a white paper on our website. If you want to dive more into the technique that we apply here, you can read through that. Well, the most critical impacted territories are actually the polar regions and areas around the geomagnetic equator. So you can see on the right side, the Earth with this red band, and that red band is crossing South America, Central Africa, and some regions in Asia. So those are the most critical territories impacted by the degradation due to the solar activities. Now, another exciting technology included in our latest release of POSPac Complete is the Trimble RTX NMA. As you probably know, that the GNSS messages are very vulnerable. That means we've been seeing rising threats of GNSS spoofing and signal manipulation, and that can lead to significant positioning errors. Now, with this Trimble RTX NMA authentication that we built into the messages, we can ensure the GNSS signals are originating from legitimate satellites, protecting workflows from spoofing. In POSPac Complete post-processing, this is achieved by directly downloading Trimble's pre-vetted, verified ephemeris data, where corrupted broadcasted ephemeris get overwritten to ensure a fully audited SBET file gets produced. So a very advanced technology. Next one, I'm very excited to make that announcement here as well. Again, with our latest release that came out last week, we also support visual odometry. What is visual odometry? So this is a method that utilizes precise delta positioning and orientation measurements derived from cameras or LiDAR to provide continuous trajectory aiding. So again, this becomes an aiding sensor by using delta position and delta orientation that's fed into the IN-Fusion Plus engine, and the IN-Fusion Plus engine can cope with it. And this becomes very important in GNSS denied or GNSS critical environments. Now, how does it work? The observables, these delta post observables, they can be code locked into the native Trimble file format T04. and POSPac will automatically extract it and will use it in the post-processing mode. Or the user can create a specific file, an ASCII file that contains the observables. And there's a technical note out there that describes the format. It's on our customer hub site, so you can download that and look into this one. Again, this visual odometry aiding reduces trajectory drift. It can also eliminate the wheel-based DMI, which has always been a bit of a headache sometimes for customers, and error-prone to slippages, to tire pressure, etc., etc. Now, this feature is just included as a standard feature in POSPac Complete 2026.04, and obviously the next ones. It would support also the estimation of the lever arm of that aiding sensor. And again, it has the 6 DOF approach, so that means 6 degrees of freedom. So we support 3 data positioning information and 3 data orientation information to be added to the aspect generation. Now that brings me to LiDAR-QC. Well, LiDAR-QC tools are not really new. They've been out in the market for a long time, but I just wanted to send a reminder on how powerful LiDAR-QC tools are. So the main goal here is really to create consistent and homogeneous point clouds by using a trajectory adjustment approach. So we're using the LiDAR system as an aiding sensor to improve the aspect robustness and reliability. We're supporting that in the mobile mapping sector as well as the uncrewed airborne sector, and it's totally hardware agnostic. Okay, so you can think of our LiDAR-QC tools like an advanced version of LiDAR simultaneous localization and mapping. So just to repeat, main function is really to create a corrected trajectory by having LiDAR as an aiding sensor. Very helpful in critical terrain, GNSS critical environments. We can also calibrate the bore set angles between the inertial measurement unit and the LiDAR, and we can create a last point cloud file. Now, just some pictures to show you the effect of before LiDAR-QC and after LiDAR-QC. This one here is from the mobile mapping, segment. On the left side, you can see the scene was recorded like second time, or it can be like multiple times. You pass the vehicle passes the same scene a couple of times, and you could see a mismatch in the point cloud. So you can see on the parking lot here, it does not match horizontally. After LiDAR-QC, on the right side, it matches perfectly. Here an example from the uncrewed airborne sector. On the left side, before LiDAR-QC, so you can see that the building has very noisy walls and the roof shape is not very clear. On the right side, after LiDAR-QC, straight lines for the walls and the roof is really showing the proper shape. And eventually also a very recent data set from the marine side. You can see on the left side where the data were collected, basically under bridges. So as soon as you go under a bridge, you are exposed to multipath effects, you are exposed to GNSS denied areas, etc. Collecting LiDAR data there means as soon as you are next to those buildings or below a bridge, you may not have perfect GNSS positioning information. That means you not have a very good point cloud. Now in the middle here, you can see the point cloud results before LiDAR-QC, while the scaling here, the color scaling, goes from 0 to 10 centimeter vertical standard deviation. So that means all these red dots there, they're not perfect, right? So they are extending the 10 centimeter level of accuracy. Now, after LiDAR-QC, on the right side, you can see that most of those red dots are basically gone. And that's the job that LiDAR-QC does. Applicable to mobile mapping, uncrewed airborne, and marine world. Now, another thing that we achieved within LiDAR-QC is also very recent. Specifically for the Trimble Applanix products, we have a new point filtering method there that basically cancels all of the points that we don't need for the trajectory adjustment process, which means we are using less RAM. So we save 20% of RAM, and we also accelerate the processing. So speed improvement is also around 20%. This is an average, really depending on what data you typically load. Now that brings me to Camera QC BST, and that's the moment where I hand off to Mohamed to say some words about our exciting Camera QC tool.
Thanks, Nico. Let's start by identifying what Camera QC does in general. It does three functions: bore side calibration, camera interior geometry calibration, and finally, trajectory accuracy optimization. And it does that in two modes, either if you fly a dedicated calibration flight or you're flying a mapping job and you acquired a few thousand images. You can take 50 or 60 of those images and run them by Camera QC for quality control purposes. It gives you that peace of mind that all of your calibration parameters are intact, and you could do that in different spots and different mapping projects. Now, Camera QC BST in general is developed for the fast and furious processing without a user interface. How would that help the end user? If you have a large data set and you want to QC a small piece of it without having to have a user interface, which actually prevents you from measuring ground control and checkpoints and stuff. You just wanted to have that peace of mind of getting a relative quality control measure of how the data itself is performing, is doing in your Camera QC BST in the background without having to set up a project or deal with the interface or deal with ground control and checkpoints and their datum issues and so on and so forth. So the BST version, since it doesn't have that user interface, it works easier and faster, and data processing takes place in the back end of the software, so the user doesn't interact with it whatsoever. And the advantages in the latest release is that there are a few features that were added, actually, including the automated kappa kernel rotation, as well as the automated ground height extraction. It has some better pricing than the full Camera QC. It is actually a batch command line, so it adds that support for system integrators, and it has that newly produced report, so it is auto-loaded, and it saves the event and photo ID files, and it produces the adjusted EO, and also allows the user to use any previously matched type points in the operation. And that concludes the Camera QC part. Back to you, Nico.
Thank you very much, Mohamed. Along this line, and a little bit connected, what we also did is we modernized the so-called project file that we can output from POSPac to have a very elegant handshake with the Trimble Photogrammetry software, which is Trimble Info or the Trimble UAS Master. So that file has been modernized. It supports single as well as multi-head camera constellations such as the Ultracam Osprey or the PAS 880 camera. And we bake exterior orientation into it, interior orientation information into it, some metadata, and the images are even pre-initialized when you load that into the Trimble Info software. So it's basically a one-click function, and it's a very elegant thing to just take the EO values from POSPac and bring it into photogrammetric software and continue your photogrammetric job. Now, one other project or another thing that we decided to do for POSPac Complete is to create a so-called all-in-one term license. Now, this shift to the all-in-one POSPac Complete license, so we call that, was motivated by customer feedback and a desire to simplify the business model while offering more value. So the all-in-one license removes complexity of managing and purchasing software, POSPac. So the new license bundles together the processing modes single base, multi-single base, smart base, and PP-RTX servers, which is a core differentiator in the market. And it bundles that together into a single offering at a price point that is significantly lower than purchasing the components individually. So you probably know that in the past, specifically post-processed RTX was a separate subscription. Again, this is all baked into the single license offering now, which we call POSPac Complete. Now, besides the annual or multi-year term license approach, which is connected to the POSPac Complete license bundle, we also offer the auto renewal option for the term licenses. So this removes the hassle to go through the quote or the delivery process. The license becomes an evergreen subscription if you sign up on it. So you always use the latest and greatest without any downtime or any administrative headaches. You can really focus on your job, your daily job, your production environment. Now, what happens to customers who had POSPac MMS or POSPac UAV perpetual license? Now, all of those customers that are under maintenance, they received already a free demo license if they had installed POSPac Complete or POSPac UAV Complete. And the free demo license covers the remaining time of the maintenance contract. Now, if you want to move on and switch over to the POSPac Complete permanent term license, you can pay an exclusive conversion price that is equal to the current MMS and UAV maintenance price. And not only that, you can also bundle or freeze that price for multi-years. We cap it at 5 years. However, it's a one-time conversion, so the user needs to make that decision up front. And again, he can freeze that price up to 5 years. So this applies to licenses currently under maintenance or those with less than 2 years of lapsed maintenance. If you are a user with a very old perpetual license, we also have a win-back campaign. And I encourage you to reach out to our customer success team, which is under customer success at applanix.com for further information about the win-back campaign. Another license scheme that we support is a so-called hardware-software license. A hardware-software license resides in the native T04 file, and it travels with the hardware. And the hardware being affected here is the APX RTX, the AVX RTX, and the POS LVX Plus system. And the license that we speak about is called RTX Complete. It is a subscription that enables real-time RTX to get already perfect results in real time, then post-processed RTX, single-base processing, and smart-base processing. And that without the separate traditional license that you used to see. Again, it resides in the T04 file. And that means you really don't have any license hassles. There's no transition from one computer to the other. There's no transaction of licenses, basically. It is because it's embedded, everyone can process the data everywhere at any time. You just need to have access to the T04 file and POSPac installed. Now that brings us to the second part of the presentation, which are our case studies about the hybrid area mapping. And the first case study that we run here had the objective to investigate the alignment between camera and LiDAR data that are generated by the Ultracam Dragon 4.1, so the hybrid area mapping system. And when we look at this alignment, we compared really against ground truth, so against checkpoints, survey checkpoints. And for this case study, we used the traditional single base processing. Now, my first question to Mohamed on that end, what are the challenges, Mohamed, associated with achieving high precision alignment between LiDAR and image data on the ground?
Well, the LiDAR in concept and in principle operates in a 3D world. From the moment the data is acquired until it's actually processed, it is in a 3D world, as long as you stay in a global frame of reference when the data is produced. While imagery, no matter what you do with the imagery, the final end mapping product is kind of flattened onto a 2D map projection. Even though no one is printing 2D maps anymore, but the final models in the map production environment are typically projected on a 2D map. And an example, the UTM globally or the US State Plane Coordinate System. Also, the alignment is complicated by a whole number of factors. For example, if misalignment between LiDAR and imagery happens between the LiDAR point cloud and orthophoto mosaics, the inaccuracies in the elevation model that are used in producing the orthophoto mosaic affects the alignment. If you're doing area triangulation, poor image texture will affect that, hence will affect the final imaging mapping product that when compared to the LiDAR data will result in misalignment. If you flew in Mexico in the summer versus Oslo, Norway in the winter, the weather conditions will influence the sensor assembly in general. As a result, it will influence the results, the mapping products, hence misalignments. Camera geometry, including base to height ratio in the cameras, particularly for the multiple camera systems, and that's quite the norm today. It's almost the standard in the aerial survey industry to use a multi-head camera system, and typically they include a nadir component and a bunch of oblique components. And to achieve the consistent ground sample distance, you end up with different focal length between the nadir camera and oblique cameras, hence different base to height ratio, hence camera geometry difference, and that has an influence as well. Lens distortion calibration, even though it gets taken care of really well in a terrestrial environment by the professional society, you end up with residual lens distortions, and those are really high, or the highest of those residual lens distortions is at the edges and particularly the corners of the imagery. Calibration differences when you change the aircraft. So you have one system and you have two aircrafts and you move the system from one aircraft to the other. I wouldn't say there is a necessity, but it's kind of preferable to have the calibration and a flight dedicated to calibration to catch some of those differences based on the mounting system and such. So all of the above contribute in a different shape and form and result in misalignment between the LiDAR and imagery.
Yeah, very, very good, Mohamed. That makes sense. A lot of insights here. So first question for Bernhard today. So why do you think this is important, and are you able to provide a practical real-world example?
Yeah, good question. So to benefit from the advantages of the hybrid data capture, so advantages like identical time of capture or one trajectory, it is very important that both data sets match, because otherwise offsets can cause quality issues in the data that you produce out of the data that was captured with the hybrid system. Yeah, and an example. So such data can be used, for example, for combined dense image matching with image data and LiDAR data. So that means both data sets are being used to create a digital surface model. Or another example, it could also be used for creating LOD2 building models, where the geometry, the LiDAR data is being used to create the blocks for the buildings, and the image data is then used for texturing. And it's pretty obvious there needs to be good alignment in such case so that then the texture matches well the geometry.
Okay, very well. That makes sense, Bernhard. And let's go to the next slide. And that gives you the opportunity to give a little insight on the Ultracam Dragon camera that was used for the case studies here. Please proceed.
Yeah, just a quick overview here. The Ultracam Dragon is a hybrid sensor system from Vexcel Imaging, and it includes high-quality cameras and a LiDAR. It is usually carried by manned aircraft, so this is not a system for drones. The cameras capture imagery in nadir and 4 oblique directions, so forward, backward, left, and right obliques. And the oblique images are RGB, and the nadir image is available in RGB and near infrared. So next slide, please. Now a quick look at the LiDAR that we have integrated into this system. So this is a LiDAR scanner from Regal. This LiDAR is based on a rotating mirror with 5 faces, which allows to scan permanently at 5 different angles, looking forward, backward, and in true nadir direction at these angles that you see here in this diagram.
Okay, thank you very much, Bernhard, for the introduction of that. So let's continue with the case study here. What was the setup? We collected data in 2 different regions. One data set was collected in Greeley, that's in the US. It covered 644 images. And the other data set in Austria, in the village called Gleisdorf, which is close to Graz, so the head office of Vexcel Imaging. And the number of images was about 439 in this case. And that translated into 9 LiDAR strips on the US side and about 10 LiDAR strips in Austria. Now, in terms of the setup, as we said, the Ultracam Dragon was used, and this system was equipped with an AP+60 GNSS INS system. The ground sample distance here was about 5 centimeters. The system was flown at an altitude of approximately 1,000 meters above ground, and that resulted in a point density of 31 points per square meter. As I said before, for this case study, we used base station data close by. They were both within a range of 20 kilometers to minimize the GNSS error budget. Of course, all of the lever arms, so the GNSS antenna, IMU, LiDAR, gimbal, camera, that was all known and accurately measured. When it comes to bore side calibration on the camera side, we used Camera QC as it was introduced by Mohamed. And for the LiDAR bore side calibration, we used the Regal software right process. In both terrains or sites, we had checkpoints or ground control points laid out, 13 and 19. I believe 13 was in Austria, 19 in the US. Of course, we used the same aspect file for the last point cloud generation as well as for the exterior orientation generation. Now, first thing that we discovered and that we also looked at is a so-called vertical data shift. Horizontally, we haven't seen a shift, or it was negligible. Vertically, we've seen a height shift in Gleisdorf and in Greeley, different because we are in different locations. So in Gleisdorf, we have seen 10 centimeter shift, and in Greeley, it was about 3 centimeter shift. The good thing is, the exciting thing is that we saw the same height shift for the camera data as well as for the LiDAR data. And that, in consequence, tells you already on how good the data did match, because again, we've seen exactly the same shift by an accuracy of a centimeter. So 10 centimeter and 3 centimeter. Now, a vertical datum shift or a datum shift is always a kind of a concern to users, we know. Mohamed, what are the underlying causes of a datum shift?
Well, it all starts with the same discussion we had a few minutes ago about mapping, which is really the bottom line here is that we're mapping a planet that is 3D in nature, but because of the legacy mapping algorithms and approach in general that is implemented today in every single little municipal office, state or provincial government, or even federal governments around the globe, that everyone uses maps that are projected on a specific projection, and each country has its own map projection mechanism that is used by the local authorities and such. So changing that entire ecosystem around the world, I think it's not really possible, at least in our lifetime. So maps have to be produced in 2D, or some of the mapping products have to end up being produced in 2D. As a result, you end up with flattening all of that 3D information you get from your survey data onto 2D that implies the map projection. Example is the UTM map projections and so on and so forth. The trick with those map projection is that you end up with distortions, and that distortion is not uniform. For example, in the UTM world, they have zones in there. So they broke up the entire spheroid or the entire surface of the planet into little zones. Each zone has a central meridian. That central meridian, by the way, is distortion free. You don't have any errors in there. But the outer edges have the highest distortion. So if you're flying over a few zones in one mapping area, you're going to see a variety of distortions just because you're crossing the zone lines. In the meantime, the map projections apply scale factor to the latitude and longitude, but not to the height or the vertical component. As a result, your datum shift in the vertical component is almost always the highest. So when we process any data from an aerial platform, you end up with the vertical error almost the highest at all times. Now, in addition to that, you have yourself the focal length inaccuracies that correlates directly with that vertical datum shift because it's in a vertical direction. But in the meantime, it has that issue with the scaling with the map projection. So you end up with three factors in the same direction, which is the vertical direction, the map projection influence, the focal length calibration or focal length remaining errors, as well as that vertical datum shift.
Okay, but are there any methods, Mohamed, to lessen the impact of the datum shift?
There are always two approaches to take care of a problem of that nature. One is the pragmatic one, simple, practical solution. The other one is to get to the root cause of the problem. The theoretical one will take a lot longer time and not as practical as the pragmatic one. So the pragmatic one is to pick one control point in the local mapping area and use that control point to fix that datum shift issue. Theoretically, the one control point will take care of business. However, in practice, it's more known to have, or more practical to have, four corner ground control points to have enough redundancy and to maintain and to have extra information because of that redundancy that will allow you to even assess the accuracies based on the four corner control points.
Yeah, I think, yeah, when it comes to removing that effect entirely, that's going to be a hard job, right? But are there any ways to eliminate that effect completely?
Yes, and that is actually something that I would like to really describe it simply as the new aerial triangulation of the 1970s, but to address both imagery and LiDAR in the form of merging all of the streams of data in a sensor fusion mindset that is 100% relative. So all of those LiDAR ranges before they become LiDAR point clouds, all of those pixels before they become mapping products, and the trajectory data, the exterior orientation information, to be blended properly to end up with zero misalignment between the end mapping product coming from the imagery and LiDAR.
Okay, thank you very much, Mohamed. So let's proceed and have a look at the direct georeferencing performance that we achieved. So the results that you can see here in that table, they still include the vertical datum shift that we have seen, okay? Because it's direct georeferencing, so we pretend we don't know at that time. Now, from the image side, if you look at the first two lines here, Gleisdorf camera and Greeley camera, horizontally, we achieved 4, 5, 6 centimeter. If you remember, ground sample distance was 5 centimeter. So that's 1 pixel. And in the vertical component, we achieved 11, 12 centimeters. So that's around 2 pixels, if you want to say. Now, this is out of 208 and 289 stereo model measurements. So very high redundancy. A lot of points were measured in all of those overlapping images to derive that statistics. Now, in terms of the LiDAR data, we achieved a vertical accuracy of 12 centimeter for Gleisdorf and 4 centimeter for Greeley. That was out of 63 and 78 point measurements in the point cloud. Now, you wonder why Gleisdorf is worse than Greeley? Of course, we've seen that there's a datum shift here. So that 12 centimeter is definitely impacted by the vertical bias that we have seen before, and we haven't removed it here. Now, let's have a look how the statistics improve as soon as you remove the datum shift. In terms of the image world, we are now down to 2 or 3 centimeter. So that's half a pixel and sometimes better. Vertically, 4 and 3 centimeter, which is below 1 pixel accuracy. And on the LiDAR side, we brought it down to 3 centimeters in both locations. So if you look at the numbers, it is very consistent, right? Now, as a summary of the first case study here, we've seen that the vertical bias between image and LiDAR is identical in both datasets, different regions. That proves a good match of the image and LiDAR data. The vertical accuracy between image and LiDAR world is identical after the datum shift is removed and after, let's say, a relative error triangulation without any ground control points. Again, relative error triangulation means no ground control points. So what does that mean for our accuracy? What we have seen is direct georeferencing, 1 pixel accuracy horizontally, 2 pixel vertically. For the LiDAR data, 3 centimeter at an altitude of 1,000 meter. And when you run a relative error triangulation without any ground control points, you even improve the accuracy in the image world down to half a pixel or 3/4 of a pixel. Now, Bernhard, does this outcome align with the anticipated performance of the hybrid aerial mapping sensor?
Yes. So these numbers meet the expectations that we have based on theoretical considerations and also on measurement results in our calibration lab. The results are confirmed by a number of projects and tests around the globe, also in other project areas, not only these here. And they're also shown in repeated data capture, always in the same area. So in the Gleisdorf area in Austria, close to our office, this is captured multiple times, again and again, and we can confirm these numbers there.
Yeah, perfect. And as we have seen also from the different terrain or different regional data set, it confirms the same performance, and that's very exciting, I think.
Yeah.
Right, that brings us to the second case study. And here we wanted to focus on the accuracy assessment, again, about LiDAR and image data, by using the IN-Fusion PP-RTX processing mode that I had mentioned a couple of times in the presentation today. So we compared the single-based processing mode, like the traditional single-based processing mode results, against the IN-Fusion PP-RTX for those data sets. Now, Mohamed, could you maybe elaborate on the factors that distinguish post-processed RTX as a unique market leader and a key differentiator?
That could be addressed in a few categories. For example, the cost category. when you address a wide area mapping project or a corridor mapping project and you are in a planning stage, especially if it covers statewide or countrywide in Europe or overseas in general, you end up with infrastructure cost or initial cost, which is buying those base stations. So the single base station is part of the initial cost. While when you use the RTX, you're covered because you don't have to buy your base stations. In the meantime, there is associated logistical cost with it, which is the hardware, moving that hardware around, and the setup time and the labor cost, and then security in some parts of the world, because in many parts of the world, sending boots on the ground is not safe. Hence, you need security to go with that. While with the PP-RTX, you don't need any of those logistical costs to be included. You're purely operating with a software subscription and using 100% cloud-based approach. The other factor that is, to me, particularly important with the area surveys is the baseline limit. So with the standard differential GNSS or PPK or whatever naming convention, when you have a baseline, dedicated base station on the ground and your aircraft is flying, acquiring area survey data, you have a baseline between that dedicated single base and your aircraft. That baseline shouldn't exceed 20 to 30 kilometers. If your aircraft is further away than 30 kilometers, there will be some repercussions and basically accuracy degradation. And to try to deal with that while you're still using the base stations, you will need multiple base stations. All of that planning is not really necessary whatsoever when you're using PP-RTX. So if you have a large wide area mapping project or a large corridor mapping project flying around for hundreds of miles or hundreds of kilometers, you need multiple base stations. And on top of that, you need some strategic or critical thinking how to plan the project this way and such. With the PP-RTX, you have the peace of mind of actually flying anywhere free without any planning necessary to cover all of the above mentioned topics. And you end up with the data coming your way from your cloud using your software, and it takes care of producing the solution for you. The last type is actually the last category is the convenience, because when you're operating in a PP-RTX environment, all of the frame of reference business, all of the geodesy and its influence on your data is taken care of automatically in the software environment. While if you have your own dedicated base and you're operating in two different countries, for example, and which happens very frequently, especially if you are in a European ecosystem, if you're in a Latino ecosystem, people fly all over the place between different countries and they end up with different frames of references or different datums, and you have to take care of that with subject matter experts to make the data processed properly. While in the RTX business, you don't have to deal with any of that because it's done automatically in the software for you.
Thank you very much, Mohamed. So Bernhard, in what ways does the PP-RTX provide value to your clients and support your Vexcel data program, in short, VDP?
Yeah, so I can just reiterate all the advantages of PP-RTX that Mohamed was already describing. So that adds a lot of flexibility to all the projects. So with regard to VDP, so Vexcel Data Program, VDP is using PP-RTX as the default processing approach, and it allows to highly automate the workflow. And just in case, we have a backup strategy with using single base processing in case of any issues. The workflow is very robust, so that typically at least 9 out of 10 projects can be processed with PP-RTX, if not more. And just to give you some context, we produced 6 million square kilometer at 15 centimeter GSD or better in the year 25, so last year. So it's a huge number that we capture and process every year, and we are all doing that with PP-RTX, and it's quite successful. The data
thank you.
production at BDP meets very high standards, so that means that all of that is then also controlled with ground control points.
Yeah, thank you very much, Bernhard. That's very impressive, I confess. So to continue on this case study, so this is a simple graph that shows you the direct aspect trajectory comparison between the legacy single base approach and the PP-RTX approach. We are seeing the RMS is around 2 centimeter. And what does that mean in the real world when we held the checkpoints against it? So direct georeferencing without any datum shift, and for the camera data, you can see that we achieved the 1 pixel accuracy, whether you use single base or PP-RTX, 1 pixel horizontally and 2 pixel vertically. So Bernhard, how do these findings align with Vexcel's observations regarding direct georeferencing performance?
Yeah, so when speaking of direct georeferencing, we are typically thinking of 2 options. The first approach involves the least possible amount of processing. It means that the orientation of image and LiDAR data fully depends on the processed GPS data. And the second approach involves basic processing steps like the collection of type points to position imagery and LiDAR relative to each other. And in the second case, we typically see blocks that are very stable, meaning that type points link the images in a good way, and the processed GPS locates the block in the world. Consequently, the relative orientation depends on the image and LiDAR data, and the absolute orientation on the GPS data in this case.
Okay, so but those results are here direct georeferencing results, right? So no error triangulation, etc. Mm-hmm. What are the typical applications where the direct georeferencing is used?
Mm-hmm. Yeah, so we see the big benefit in the potential for high automation of the workflow. This is also where we at Vexcel use it. So we use it for rapid response applications where time is critical, for example. So that means we are doing mapping of natural disasters, and in such projects it's very often just not possible to capture GCPs, and most important, it's very important to deliver the data in time, and more important, to have a timely data delivery than a very high positional accuracy. So therefore, as availability of the data is key, we rely in this case on direct georeferencing.
Okay, and what are the applications then, Bernhard, that require really the error triangulation with or without GCPs?
I would say that as soon as stereoscopic measurements are needed, then an error triangulation is needed. And with that, I mean that type points are used to link the images. So this is because for such measurements, the orientation of images to each other is key. Then it depends on additional project parameters, if GCPs should be used or not. For example, large auto projects will require GCPs to make sure that auto blocks can be well aligned and matched to other blocks, other data, while local infrastructure projects might also work without ground control because they are just local. So it fully depends on the project parameters.
Okay, thank you, Bernhard, for that insight. Very interesting. So just to conclude on this one, of course, here also the direct georeferencing results between single base and PP-RTX when it comes to the LiDAR world. And as we have seen before, the 3 centimeter vertical accuracy is what we achieve. It really doesn't matter how you post-process the data. Again, an argument for the replacement of the single base processing option versus PP-RTX. So PP-RTX is strong enough to do the jobs, and you learned all the benefits from it. So final summary of that case study of the direct georeferencing single base versus PP-RTX. We've seen that the IN-Fusion Plus PP-RTX matches the absolute performance of traditional single base approaches, and it is a very consistent, you're getting a very consistent performance globally, basically through a single button function, right? And I can just only repeat that image and LiDAR world matches pretty nice. So in the direction of referencing, we've seen 1 pixel horizontal accuracy, 2 pixel vertically. On the LiDAR side, 3 centimeter vertically. And after an error triangulation, again, without any ground control points, you are getting sub-pixel accuracy. Just as a note, when it comes to the vertical RMS in the image world, directly referencing in the image world, that this is also a function of the height-base ratio in the image world. You're not measuring right straight to the ground like a LiDAR system, so you still have the geometry of the images and how the rays intersect on the ground, and that impacts obviously the vertical accuracy estimation. So that brings us to the Q&A session, but it looks like the presentation was longer than what we anticipated. So I think we would skip that part, unless, Mohamed, you have like a single interesting question from the Q&A box that we want to answer here, and the rest of the questions we'll take it directly with you via email. Is there anything that is exciting to bring up, Mohamed?
Actually, there are a few questions there that, as you mentioned, we will address by email, and I will address a couple here by texting on the platform, and the rest by email. But there is a question that is actually fast, and you could answer it quickly, Nico, if you don't mind, by Ronald, asking, having an AP20 based system, am I okay to use In-Fusion Plus processing instead of In-Fusion?
Yes, of course. It's even recommended because, as I said, the In-Fusion Plus engine can really use all of the recent GNSS signals and frequencies, especially when it comes to the Baidu 3 satellite generation. There's the B1C and B2A signals. They are very, very helpful. And it's only the latest engine that can cope with all of those frequency, and it's robust, stable, and that's highly recommended for all of the different business lines, not only mobile mapping industry, but all of the different business lines, whether it's marine, land, or airborne.
Thanks, Nico.
Okay. Yeah, thank you, Mohamed. So that brings us to the end of the session. So sorry that we extended it a little longer, but I hope it gave you a valuable insight on our POSPac Complete products on the hybrid aerial mapping. And I wanted to thank you, Mohamed and Bernhard, to join the session. It was a pleasure to prepare it, and it was a pleasure to conduct it. And thank you very much also to the audience to see that. Again, this is going to be recorded, so you can access it later on as well if you want to revisit. Otherwise, reach out to us, reach out to techsupport@applanix.com, or reach out to Mohamed, Bernhard, or myself if you have any other questions. Thank you very much again, and have a great day. Bye-bye.
Thank you. Bye-bye.